All right, welcome to The Explainer. Today, we are diving straight into something absolutely fascinating, the architecture of artificial minds. We're going to trace the evolution of neural networks, starting from the biological blueprints literally sitting inside our own heads, right up to the massive deep learning structures powering today's AI. Think about this for a second. How exactly do we teach a machine to remember the past? It's a pretty profound question, right? Building an AI that can process sequences and actually learn over time, well, that's historically been one of the biggest, most fundamental challenges in computer science. So let's break down exactly how engineers are solving this giant puzzle step by step. Okay, part one, the biological blueprint. To really understand these machines, we've got to look at ourselves first. Our own biological neural networks are made up of neurons, right? Signals travel from the dendrites through the cell body and shoot down that long axon to the synapses. Now, this electrochemical process moves at about 3 meters per second. Honestly, that is incredibly slow compared to a modern computer chip, yet somehow it still allows us to perform complex reasoning that machines still really struggle to replicate. Now, when we look at the artificial equivalent, man, the biological inspiration is just obvious. An artificial node takes in inputs from other nodes, acting exactly like those dendrites we just talked about. Each input gets multiplied by a specific weight, basically saying, hey, how important is this piece of info? Then the node calculates the sum of those weighted inputs, subtracts an internal threshold, kind of like a gatekeeper bias, and if that sum clears the threshold, boom, the artificial node fires.
Moving on to part two, activating the network.
So for these networks to actually interpret messy, real-world data, they desperately need something called an activation function. Without injecting this nonlinear mathematical transformation, our neural nets would just be, well, glorified linear calculators. They literally couldn't draw complex decision boundaries. Think about trying to draw one perfectly straight line to separate all images of cats from dogs. It's mathematically impossible. Real-world data is curved and complex, so activation functions let the network bend and flex to match that reality. Engineers actually rely on a whole cast of these activation functions, depending on what kind of math the output needs. You've got the sigmoid, which cleanly squashes values between 0 and 1. There's tanh, stretching from -1 to 1. Purelin gives you a linear output, usually right at the very end of the network. Soft plus creates this nice smooth curve to prevent dead neurons, the ones that mathematically get stuck and just stop responding entirely. And of course, the incredibly popular ReLU, or rectified linear unit. Consider the elegant S-curve of the tanh function. By mapping inputs from -1 to +1, tanh can handle a much wider spread of data than the sigmoid function. It scales extreme numbers way down, which totally prevents the network from freaking out and going unstable during crunch time. But the absolute coolest part? Because it drops below 0, it perfectly captures negative data correlations. It literally teaches the AI to understand when two things are complete opposites. All right, part 3, the vanishing gradient problem. So here's a huge issue. Why do deep networks suddenly just stop learning? Well, during training, a neural net uses a process called backpropagation. Basically, it sends an error signal backward through its layers to update all those weights. But it's kind of like a massive game of telephone. Over long distances, the original signal just fades out. If these mathematical gradients shrink down too much, the deeper layers stop getting any meaningful updates, and the whole learning process just completely paralyzes. And here is the massive irony of it all. The unintended consequence of those beautiful, elegant S-curve functions we were just praising, like tanh and sigmoid, they're actually the main culprits here. Because they saturate or squash input values into such super narrow ranges, their gradients shrink down to practically 0 when they hit extreme values. The network essentially just clamps down, stops updating the deep layers, and the AI totally loses track of the information. And that massive roadblock brings us to our first architectural hero, ReLU. Unlike sigmoid or tanh, the rectified linear unit is what we call a non-saturating function, at least in the positive direction. It's a really simple adjustment, but it's totally brilliant. It provides stable, non-zero gradients that shoot back through the layers like a rocket. It guarantees that deep, super complex networks can actually keep learning without the signal fading out. Seriously, this was an absolutely massive historical breakthrough for deep learning. Which brings us to part 4, fixing sequential memory. Now, while ReLU is an absolute game changer for standard feed-forward networks, basic recurrent neural networks, or RNNs, they face a totally different beast, the dimension of time. If a sequence of data, let's say a really long paragraph of text, goes on long enough, the distance that error signal has to travel backward through time becomes literally impossible. The gradient fades out over the sequence, and the machine literally forgets the beginning of a sentence by the time it reads the end. Not great. Enter the saviors of sequential data. To fight this fading gradient over time, engineers came up with these super ingenious specialized gate structures. You can kind of think of them like really strict bouncers at a club, selectively deciding exactly which pieces of information get to stay in memory and which get tossed out. The two heavy hitters using these gates and the long short-term memory network, the LSTM, and the gated recurrent unit, or GRU. Let's get into part 5, the LSTM versus GRU showdown. When you stack these two up side by side, the architectural differences jump right out at you. The heavy-duty LSTM relies on a really complex 3-gate system, an input gate, a forget gate, and an output gate, all running alongside a completely separate cell memory state. But then there's the GRU, which is this beautifully streamlined variant. It bundles all that information management into just 2 gates, an update gate and a reset gate, and it carries the whole shebang efficiently in just a single, unified, hidden state. And the number 2 is absolutely crucial here. Representing those 2 gates of the GRU, this single structural difference is exactly why the GRU has way fewer trainable parameters than its bigger, heavier rival, the LSTM. And dropping that one gate creates this awesome cascading effect of benefits. It gives the GRU a massive edge in efficiency. Because there's one less gate, it means way fewer complex math operations inside every single unit. So the GRU is simpler to code, it trains so much faster, and it's incredibly memory efficient. At the end of the day, that saves researchers and companies a ton of computational power and time compared to running the heavier LSTM models. So what's the final verdict? Well, it really just comes down to what your specific project needs. If you're wrestling with highly complex data where capturing very long-term dependencies is absolutely critical, like, say, translating an entire novel from one language to another, the heavy-duty LSTM is probably going to be your go-to. But if you need rapid computational speed, memory efficiency, and you just want to get your model trained faster, the streamlined GRU takes the crown for sure. Which leaves us with a pretty fascinating trade-off to think about: speed or memory. As these artificial minds keep evolving and scaling up to sizes we couldn't even imagine a few years ago, which of these two architectural priorities do you think is going to drive the next massive leap in AI? It is a crazy balancing act between the computational efficiency and long-term retention. Thanks so much for joining me on this explainer, and keep questioning the algorithms that shape our world.